Okay, hi everyone. My name is Todd Wilde.
Bring it down.
Bring it down. Bring it down. I'm the Director of Technical Computing in HPC at Mellanox. I'm going to talk to you about new accelerations for parallel programming. First, I'd like to thank the HPC Advisory Council for having me here. I was telling someone the other day that I, many years ago, spent my honeymoon in Spain, so it's always nice to come back. I have very fond memories. So I'm going to talk about a few different topics. First, I'm going to talk about the co-design architecture for parallel programming. Then I'm going to give an introduction to PGAS languages. Talk a little bit about some of the accelerators that we apply to these PGAS languages, such as FCA, which is our Fabric Collective Accelerations. And then I'm going to talk about a joint collaboration that we've done between Mellanox and HP that explores InfiniBand scalability for one-sided communications. So first I want to talk about the co-design architecture. What is the co-design architecture of Mellanox? So this came about as a problem that we wanted to solve. And the problem was that we saw the bifurcation of the development between the hardware and the software of a networking environment, a networking stack. So at Mellanox, we were very much concentrated on hardware development and providing very efficient, fast networks for the server platforms. And what we saw is that the software development of the communication libraries was being done separately from our hardware. In other words, we weren't involved very much in the actual application and communication library programming to the networking interface. So what this does is it causes bottlenecks between this software and this hardware interface. So we have this network here that provides very high throughput, very low latency characteristics, and also provides a lot of offload mechanisms. And we see that some of the software implementations, there's many different MPI and PGAS implementations, and some of them really are just writing up here, not being aware of all of the offloads and accelerating capabilities that the hardware can provide. So what we've really been trying to do at Mellanox for the past year with our co-design architecture is kind of move up the stack and extend into the MPI and into the PGAS languages. So to provide various capabilities of taking advantage of the collective offloads, taking advantage of the various transport mechanisms that InfiniBand can offer, taking advantage of the RDMA capabilities of InfiniBand, and moving all of those hardware capabilities into the software layer. So this is a representation of this stack that we've developed. Here we have the InfiniBand verbs layer. This is the hardware layer that the HCA card exposes up to the software. So we've maintained this InfiniBand verbs interface because we feel like it's a very powerful interface, a very rich interface, and we want to continue to use that. But what we've done is we've developed a set of acceleration products that sit between this interface and the MPI or the SHMEM or the PGAS language. So this is really made up of two different accelerators. The first is called MXM. This is Melanox Messaging. This is providing accelerations for the underlying send and receive messages that the MPIs and the SHMEM programs use. It has a number of features within it. It provides reliable messaging optimized for Mellanox HCAs. It provides a hybrid transport mechanism. So depending on the scale of the cluster and the size of the jobs, we can select different transport modes that best match the type of scale that's being used. For instance, Dr. Panda talked about the difference between RC and UD. Reliable connections can provide lots of nice features and really good performance characteristics, but as we scale into much larger systems, we may want to go to some type of connectionless mode, like an unreliable datagram, to get the performance at large scale. We also offer efficient memory registration, receive side tag matching, support for large pages, and a number of other features within the SendXM. The other package is called FCA, and I'm going to go into this a little bit more in depth further on in the presentation, but basically FCA is the Fabric Collective Accelerations. So the MPIs and the other parallel programming languages use things called collectives. And a collective operation is basically an operation across all of the jobs in a particular, or all of the processes in a particular job. So FCA provides a number of features to accelerate these collectives, such as topology-aware collective operations, taking advantage of the hardware multicast capabilities in InfiniBand, using separate virtual fabrics that only the collective runs on, and also supporting our core direct hardware offload, which is a mechanism where we actually run the collective operation in the HCA hardware. So our goal with these two MXM and FCA accelerators is to push those into lots of different MPIs. So Open MPI is supporting them, Platform MPI is supporting them, a number of the commercial MPIs supporting them. We also are looking at, or we have also pushed them into the Open SHMEM standard, so we have an Open SHMEM product that uses these, and we're also pushing them into various PGAS languages such as UPC. So the goal is take the burden off of the MPI developers and provide these accelerations that properly use our hardware to get good performance results. So now I want to talk a little bit about PGAS languages. Dr. Panda had people raise their hand if they knew what MPI was. Does anyone know what PGAS languages are? Okay, PGAS is very new types of languages, and they're really a higher level of abstraction or a higher level of abstracted parallel programming languages than MPI. And I'll briefly show you how they work. So PGAS stands for Partition Global Address Space. It's really providing the best of both worlds. It provides message passing, much like MPI, but it also provides shared memory methods as well. It's an explicitly parallel programming model with single program multi-data parallelism, much like MPI. So the way that it works, it runs a single program on multiple processes, much like MPI does. It typically runs a single thread per process. There's a concept of global address space across the complete job. So if you look at all of the threads that are spread across all of the processes, there's a global address space associated with all of those threads. This address space is also logically partitioned. So there's a concept of local memory for a thread and remote memory for a thread. There's SHMEM, which is another programming language, is being used and proposed as a lower level interface for PGAS implementations. And you'll see a lot of different PGAS languages come up. There's some being invented as we speak, and there's a lot that are being deployed at various sites. Some of the examples of these are UPC, CAF, Titanium. Another is Chapel. I think we have a talk later on by a gentleman to talk about Chapel, which is another PGAS language. So I'm going to give the example of one specific PGAS language, which is called UPC, or Unified Parallel C. This is an open source compiler. It's available from Lawrence Berkeley National Labs and University of California, Berkeley. It currently operates over InfiniBand verbs, RC connections, via something called a GasNet interface. And the interesting thing and why I want to talk about UPC is because we've taken our accelerators that I talked about earlier and incorporated those into GasNet. So you can see this picture here of UPC. It utilizes a distributed shared memory model. So I have basically a thread, various threads, and then I have memory that's associated with that thread. So it's distributed memory. So every thread has its own memory, but then we treat it as a shared address space. It has features like having very simple statements for remote access of memory. And it minimizes thread communication overhead by exploiting data locality. So I have a concept of this memory being associated with this thread and this memory being associated with that thread. So the UPC memory model is, like I said, is divided into private space and shared space. So I have my shared memory here, and then I have my private memory here. My shared memory, anybody can access any shared memory anywhere, but I also have affinity, so I have an area of that shared memory that's associated with my thread. So how do I write a program using UPC? Basically, I use a shared qualifier when I declare my variable. And when I do that, that variable gets spread across all of that memory, that distributed memory. So I have a couple of examples here. Here's where I declare a variable array1. And when I say shared, I give it a field here which says how I share this variable across all of the distributed memory. So here I say I want to share it one element into each thread. So you can see this array is laid out. Element 0 is here, element 1 is here, element 2 is here, and then it just round robins across these three threads. So if I would have put a 2 here, it would have put 0 and 1 here, 2 and 3 here, etc. Here's an example where I just declare all of the array in one single distributed area. Okay, so I can really play around with and manipulate how this array is spread out across the memory based on this declaration. So that's the memory model. Now the execution model is these threads work independently as a single program on this data that's spread out across the distributed memory. So I have a few different variables here. I have the number of threads is specified at compile time or at runtime, and it's a program variable just called threads. Then I have another variable called myThread, which specifies the thread index that I'm actually part of. So either my thread can be 0 or 1 or 2, depending on what rank I am within the job. I also have a couple other nice functions here. I have a barrier function, which is used for global synchronization. And then I have a for loop that can help me do loop iterations. I'll explain a bit later. Another thing to note, there's two compilation methods. You can do static threads mode, where the thread is number of threads is specified at compile time, or you can specify it dynamically at runtime. So let's look at a couple simple examples. Here's a very simple example of my first UPC program. Basically, what I say is if my thread equals 0, I print this out. Receiving starting execution from the number of threads and then my thread. So this is a way to say that this printf is only going to be executed by the rank 0, or the first process in all of the list of threads. Now here's a little bit more of an interesting example, and this shows you how you can get parallel scalability when you run a particular math operation using UPC. So here I have a 100-element array, and basically I have two of them, V1 and V2, and I want to add these. So if I did this with a normal CPU on a single process, he would have to go add every single element in that 100-element array. With UPC, what I can do is I can lay this array out across these 4 different threads. Okay, so I do that by declaring it up here as a shared. And then I lay it out 0, 1, 2, 3, etc., all the way wrapped around. And I do that for V1, V2, and V3. So now you can see how this memory is laid out for this array. Now I have a for loop, and I count from 0 up to the number of threads. And if my thread equals the iteration within the for loop modulo the number of threads, then I go ahead and then execute this addition. So thread 0 is always going to execute the array element 0, the array element 4, the array element 8, etc. Okay, so everyone's going to do 25 of these operations, and we're going to have the answer here in V1 plus V2 variable. The nice thing is everyone works on their own local memory. So you can see how this localization works here. So this is a very simple, if you look, very C-based parallel program. I don't have to worry like MPI about sending and receiving data and stuff. It's all kind of done by how this memory is laid out within the threads. And then I also have a UPC for all, which is an optimization. And what this UPC for all function says is if the owner is if the owner is I, to go ahead and compute the thread as well. So you don't have to do this little check here. Okay, so that's an example of PGAS language. Like I said, there's several, but we're seeing a lot of interest in UPC. So we've concentrated on putting our accelerators into some of these PGAS languages. Today we support SHMEM, and we support UPC. Before I go into some of the performance analysis that we get with SHMEM and UPC, I want to talk a little bit about more in depth about the FCA fabric collective accelerations. So first, to understand what FCA is, we really should understand what a collective operation is. A collective operation are group communications, and they involve all the processes in a job. So they tend to be synchronous operations in nature, and they can consume many wait cycles on large clusters as we wait for all of the processes to get to that place within the collective. For instance, a barrier operation is a synchronous operation that says when every process gets to this point in my program, then I can go on. So you can tend to get lots of wait cycles on large clusters. Popular examples of collectives are things like barrier, reduce, allreduce, gather, all gather, broadcast. So some of the challenges we have with collective operations is, one is many times the collective algorithms are not topology aware. This can make them very inefficient because what happens is if we have a large cluster here, you can see with several stages, we tend to have lots of messages crossing back and forth to be able to finish this collective. This can cause congestion within the network due to the many-to-many nature of the collective itself. Also, because the collective is involved in all of the servers or many processes, your collective operation is only going to be as good as your slowest node. So things like OS jitter can really affect the scalability and also the variability of your collective operation. You could have 100 servers and you could have one server take a hit with doing something else, and your whole collective operation that would affect all of those 100 servers with that one server's OS jitter. So you really want to try to minimize this as much as possible. And of course, as the jobs scale up and we get more hundreds and thousands of servers, the percentage or it increases the odds of actually hitting this kind of behavior. So Mellanox has developed something to accelerate collectives called Fabric Collective Accelerations, or FCA. This is a package that we provide. It's actually provided free with our hardware. It's integrated into our Mellanox OFED, and you can also go onto our site and get it to work with standard OFED as well. So let's look at how this works. So the concept here is there's something called an FCA manager. Okay, this FCA manager is sitting on some type of management server within your cluster. And it builds a topology-based collective tree. So it knows what ranks are involved in the collective and where they sit within the cluster. And it builds an optimized collective tree based on that topology. It also can run the collective on a separate virtual network. So InfiniBand has the concept of separate virtual networks for different traffic quality of services. And so FCA can actually take a separate virtual network and run the collective only on that network. It also takes advantage of IB multicast for results distribution. InfiniBand has a feature called multicast where the switch actually can replicate a packet. And so FCA relies on the switch actually replicating the packets for distributing the results of the collective operation. Dr. Panda talked a little bit about that as well, support for those multicast and MPI and how it can help. Along with FCA Manager, there's FCA agents that are running on the servers. I don't really like the term FCA agent. It's really just an FCA library that's integrated in with the MPI. This FCA agent is taking cues from the FCA Manager as far as how it runs the collective. We also have internode optimizations within the FCA agent, so optimizations within the node. And we also take advantage of our Core Direct, which is a feature where the collective operation can actually be offloaded to the HCA hardware. So the FCA agent takes advantage of that feature on the HCA if it's available. And it doesn't need to be. You can run this on older HCAs that don't have the Core Direct, and it still works, and you still get many optimizations based on the other things I talked about. So let's look at an example how FCA might help a collective operation. First, I want to show what a collective is without FCA, I picked an Allreduce. I picked a summation example using recursive doubling. So here I have the numbers 1 through 8. Each one of these numbers you can think about sitting on a CPU somewhere or sitting in a processor. And I want to add these numbers up, and then I want to distribute the results. So a typical algorithm for doing that is called recursive doubling. So here, basically, I take pairs and I add them up. And I've gone from 8 to 4 with my answer. And then I go down to 2. And then I go from 1. And basically, those packets have to be sent to the different machines to get those additions. And then the CPU does that addition. Once I get my result, I send it out as a separate packet back to all the other processors. So there, my collective is finished. So that looked really simple with 8 processors, but what happens when you scale that out? So a 4,000 process Allreduce using recursive doubling takes 12 stages. So there I took 3 stages to do it. If I had 4,000 of these, it would take me 12 stages. So that's a lot of packets being sent around the network. So let's look at how FCA might do this. Instead of using recursive doubling, it uses its own FCA optimized algorithm. So here I have hosts. I have 1 through 324 hosts, and I have 8 cores in each host. So I'm going to run this job across all of those processes. So each CPU is holding a number 1 through 8 in all of these servers. So what FCA does, instead of doing recursive doubling, which might have packets going all over the place along your network to get the answer, it's going to optimize this collective based on where these processes are sitting in the topology. So first, it does all of the intranode processing. So it does the addition of 1 through 8 within the host. So no packets have even got out on the network yet. Then what it does is it builds a collective tree based on where all of these hosts sit within the network. So it's going to build a collective tree and have pick a parent as one of these hosts on this switch, and it's going to do that for every one of the level 1 switches here. So we call that first tier coalescing. That's the second stage in the operation. Now I've got a host on every one of these 18 switches that has the answer for each level 1 switch. Now I do my second tier coalescing. And in this case, I only have 2 tiers of network of switches. So I've got my result. Now instead of sending that result out as a separate send operation to each of the hosts, it uses the multicast. So it just sends 1 packet up here. And then these switches start multicasting that, replicating that packet out to everybody. So you can see this is a much more efficient way to do Allreduce at a large scale. So now I want to talk about a joint collaboration that we did with Hewlett-Packard, where we actually saw customer needs for this SHMEM and this UPC PGAS, and we wanted to see how well it would scale over InfiniBand with the deployment of MXM and FCA accelerations. So this was a joint collaboration that's actually still ongoing. The goals of the collaboration were to investigate InfiniBand scalability, performance scaling to hundreds to thousands of nodes, identify any issues with the implementation of SHMEM or PGAS with this kind of scalability, and then provide a complete solution. Like I said, we focused on one-sided communications. So we focused on SHMEM and UPC, parallel programming languages. Both of these using one-sided put and get operations for data transfers. So when I mean one-sided, MPI has the concept it's more two-sided. So there's a send and there's a receive that need to happen. Someone needs to add to the send queue, and on the send side, someone needs to add to a receive queue on the receive side. With one-sided, which is how SHMEM and UPC work, I just do reads and writes directly into the remote memory. I don't have to do any send-receive semantics. The test configuration at AP was a 128-node cluster of SL390s. These were G7 servers using Melanox QDR InfiniBand. So these were, I believe they're 12-core servers, integrated with ConnectX-2, QDR switches, cables in a fat tree topology. So the workloads that were employed here were all-to-all. All-to-all is a collective where all processes communicate with all other processes. Lots of random puts, randomly selected nodes in memory locations, and causes a lot of high stress on the interconnect. We also concentrated on short messages, because that's what a lot of parallel programming languages use. So in the range of 8 bytes to 8 kilobyte size message. We had a large memory footprint per node. We used about 80% of the total host memory just for the communications. And then we concentrated on other collectives as well, such as barrier, reduce, and broadcast. So these are some of the performance results that we got. these results were based on the SHMEM PGAS language. And basically what we're looking at here is we're looking at using Open SHMEM, which is an open standard for SHMEM, using that running over InfiniBand with and without employing the collective accelerations that we developed in our co-design architecture. So this is all-to-all bandwidth. That's all the processes talking to everyone, all the other processes. We focused on 1 kilobyte and 8 kilobyte messages using all cores on the node. And you can see the bandwidth improvement with using Mellanox MXM on 120 nodes improved about 2 to 6 times, achieving close to optimal scaling. So here's the initial bandwidth. You can see here that this is the bandwidth and this is the number of nodes. And then this is the bandwidth optimized after all-to-all. More importantly, you can see very good results such as this in the 128 byte range. Also very good scalability as we scale out to the number of nodes. You can see that the bandwidth stays sustained. This is looking at that same results on a message rate basis. Again, focusing on 8 to 128 byte messages using all cores per node. The message rate improved substantially, and this is mainly because of the MXM, using the MXM accelerations. Improvement on 120 nodes is about 15x. Again, we achieved close to optimal scaling and very flat response here. So this was before, and this was my message rate, below 1 million messages a second. And then after employing the MXM, I'm at 6 million messages a second. Okay, so this is a really good example of taking something out of the box and running it versus really applying the right tuning and the right acceleration packages to get the best performance. This is a barrier. Barrier is a collective operation. It's a synchronization. We saw a big improvement of barrier. This was employing FCA. On 64 nodes, we saw about a 16x improvement. This is before employing it. You can see that a PPN even of 1 is over almost 40 microseconds at 60 nodes. Here we have everything is below 20 microseconds. We have 14 microseconds, basically a PPN 1 out to 120 nodes. And you also, again, want to look for this flat scalability. As you add nodes, the barrier doesn't take any more additional time. This is a reduction operation, very similar to that example I showed where we do the addition. Improvement on 64 nodes was 40x. And the improvement increases as the number of nodes and the number of PPNs increase, the improvement increases as well. I think this is about a 45 microsecond reduction time. So the summary from this work is HP and Mellanox achieved substantial improvements in our SHMEM and UPC workloads. We achieved up to 16 times improvement in message rate and up to 40 times improvement on collectives. We expect higher improvements are expected on even larger clusters. And we also believe that these improvements are applicable to MPI as well, to different MPI implementations. We got close to optimal scaling and message rates. And we also, I didn't show any graphs, but we had a significant reduction in memory footprint by deploying MXM to 14 times of incremental memory improvement. So this really demonstrated a complete solution, enhancements in message protocols using MXM and FCA, and incorporated these enhancements into the product line. And the complete solution for these types of deployments is available from HP and Mellanox. So we're continuing to work on this collaboration with HP and continuing to give different results through white papers and webinars. The next thing we're doing, and we're actually doing that now, is we're expanding the investigation to FDR InfiniBand and also to HP Gen 8 servers. Okay, that's all I have. Is there any questions on this?
Does FCA support all kinds of topologies?
So today we support Factory and we support 3D Torus. SGI is also incorporating it into their MPI, and they'll support hypercubes with it.
Is it possible to apply other optimization strategies like coalescing of messages, or for example, understanding the communication pattern to try to prefetch data, or 3D sheet already, the sending of the message if you know that you are not going to receive more messages?
Yeah, so I mean, we're constantly looking at ways to improve collective algorithms. I didn't talk about it here, but we have a new HCA called ConnectID, and it does a lot of things with non-contiguous data types that are going to allow us to do optimizations, like you mentioned, for like all-to-all type of algorithms. Anything else? Okay, thank you.